much for showing up for the first session of the day. I know it's early, but you will not regret this. So I was actually the co-organizer of the tutorials track this year, and I knew the first talk that I wanted to invite, that was Brian Denton's tutorial on this topic. I think it's extremely timely, and having read the paper, the chapter, and it's really a wonderful work of, a wonderful contribution to this field and also the tutorial series. So I thank you sincerely for putting in the time and doing all this. Thank you. For an introduction, I think Brian does not need an introduction, but I will try to quickly give you his whereabouts right now. He is at University of Michigan. He's a professor and chair there at the Department of Industrial and what was the title? Department of Operations Engineering. Yeah, and he also holds titles at the medical school, professor in the Department of Urology and member of the Cancer Center at the University of Michigan. He is past president of the Informs Health Applications Society, which is co-sponsoring this tutorial session. So thank you to HAS also for doing that with us, and he's also the past president of Informs. So Brian's contributions to Informs has been, like volumes and volumes, so I'm not going to actually delay this any further. So thank you, Brian, and with that, please.
Thank you. Can everybody hear me? Thank you. What a warm welcome. Thank you for the wonderful introduction. Can you all hear me in the back? Doing okay? All right, great. Well, you're like the best conference attendees around. 8 a.m. We're getting started, so thank you so much for coming. This is a tutorial on sequential decision making in the context of chronic diseases. And so I didn't know exactly what the audience would be, so maybe I'll just do a little litmus test. How many of you are very comfortable with dynamic programming? Okay, yeah, good chunk. How about like partially observable Markov decision processes? Okay, yeah, less. Okay, great. So I'm gonna, that helps me. I'm gonna move quickly. I started right at the beginning. You can get these slides if your phone works on that QR code, and it's on the next slide here. I don't know why I love decision making under uncertainty so much. I think it might have something to do with my love of fishing, which is like a ultimate decision making under uncertainty. Where do you want to go to fish? How's it going? You collect information, you make another decision about where to go, and so on and so on. So I don't know which came first. If it's fishing that makes me like decision making under uncertainty, or decision making under uncertainty that makes me like fishing, but that's probably not really all that important for the purposes of this tutorial. But I do want to let you know that those slides, so that code, will take you to the slides if you want to follow along with the presentation, and they're up on the web, and the tutorial's going to be available too. Maybe it's already available. I think it's just been put out there. So this is your tutorial. I'm going to talk. I'm going to present. I've got lots of slides. I may not get through them all. I want you to ask questions anytime. Okay, so feel free to ask questions as we're walking through this. The tutorial is on sequential decision making, but in the context of chronic diseases. And so what are chronic diseases? These are diseases that they're not curable, but they're treatable. Okay, and there have been incredible advances in medicine that make it so people that have cancer, for example, or heart disease, kidney disease, diabetes, these can be managed for very long periods of time and very well. But there are lots of decisions that are made over long periods of time because of that. So it tends to be a very complicated decision-making process for people diagnosed with these kinds of conditions. So that's why I focus on it, because these are important, basically, and this is something where operations research could really play a role. And so in that context, I wanted to tell you just a kind of snapshot of some of the work that's been done. So PubMed, that's the repository of the National Library of Medicine. And I did a keyword search. I spent a long time on this. I don't claim that my keywords are perfect, but I'm fairly comfortable with sort of the relative levels here. So you see a lot on the left side. I would say that's predictive and descriptive analytics, if you like those terms. Lots of machine learning. Of course, that's very broad. A lot of simulation, a lot of stochastic models. All right, so like Markov chains, for example, getting used all the time. That's really like a standard methodology that are being used in medical journals for answering research questions. And then if you get over here more into optimization, there's a lot less. Okay, and so from my perspective, that's a lot of opportunity. There is a little, tiny little bar there. Okay, actually, I think that's a big deal because there's a lot of work going on. So I think if there's one thing you take away from this tutorial, it's that there's an enormous amount of opportunity.
That's 0 to 2,000, so that little bar is what? Like
Yeah, number of papers. Yeah.
Is it like 50? Do you have an idea?
I think it's 50 or less. Yeah, around 50. Yeah.
Mm-hmm.
Yeah, so I should have mentioned that number of papers in the last 10 years. Okay, so if you look at this meeting, in the program, I think we have more than 80 tracks. It's complete insanity. There's so many things going on. It's like it's a good problem to have. If you're interested in this kind of work, a keyword search on Markov decision process and health shows 247 papers. You may not be able to read that, but that's about 80 straight hours of work on MDPs and healthcare. And I missed a lot of where somebody might have said like POMDP or something and it didn't show up. Okay, so there's an enormous amount of work at this conference. So what I want to do in this tutorial is start right from the basics. Okay, Markov decision processes. This is like the fundamentals of what you need to learn, the bedrock for being able to get into more advanced approaches. And I'm going to move quickly through this. Many are comfortable with dynamic programming, but not everybody. So I'll go quickly through this, and then we'll get into some more advanced topics. And I want to spend some time as I go through talking about how the models that we use are parameterized with data. And when I talk about data in this context, it's really longitudinal data, okay, that you need for estimating the underlying models. Okay, if you want to answer healthcare questions, then how you do that, how you deal with issues of bias, for instance, are extremely important. Okay, if you care about the answer you're getting, then you can't ignore those things. And I think that's another area where there's an enormous amount of opportunity at the intersection of statistics, data science, if you like that term, and optimization. Okay, so I hope you'll walk away feeling like there's a whole world, of work that could be done. If you want, and I'm going to also try to point you to some good references to learn more. Okay, this is just 90 minutes, and I want to, give you some of my perspective on good articles to look at, textbooks to look at. I just picked some that work well for me. I don't claim it's a complete, sample. But there's a few nice papers here that give a lot of examples. So these are basically review papers that are reviewing all sorts of interesting applications of MDPs, POMDPs, and other approaches to chronic diseases, medical decision making, but also broader than that. Some of them would be looking at infectious diseases or problems around management of resources, for example, in hospitals. Okay, so these would be a few good places to get kind of a scan of some of the work that's been done. And so I think any time you talk about dynamic programming, you might want to bring up Richard Bellman. He's this, in addition to being a snappy dresser, for his time, okay? He is often associated with being like the father of dynamic programming. He certainly made a lot of contributions, came up with this cool idea that you could decompose certain problems and solve them very, very easily. He's very prolific. I think he had more than 500 articles over his career. There's some wonderful history about him. And actually, if you go back to 1954 paper he presented on this topic, he mentions problems in medicine as being an important potential future application area. And I think we're at a time now where we're seeing that kind of that area kind of grow exponentially in terms of work that's going on. So I'm going to define a few things, a few definitions. Some of you that are comfortable with this stuff will already know these. I'll use the word policy, not in the general form, but to represent like a mapping from states to actions. Okay. Sometimes you call it a lookup table, and then an optimal policy is going to be the optimal action to take for each state, and that's often what we're after. Okay, and the optimal is with respect to different kinds of goals, like could be maximizing rewards over time or minimizing costs, but there are lots of other ones too, like achieving an outcome with a very high probability, for example. A lot of different objective functions that you could have for these kinds of problems.
Question?
Yeah.
The point of treating chronic diseases is to extend time?
That's a great question.
Costs over time if you try to extend time?
Yeah, so really, I think most of these problems come down to problems that are multi-criteria. Okay, so there's sometimes a cost aspect to it. There's always a cost aspect, but also quality of life. I would say not just extending lifespan, but extending quality, quality adjusted lifespan. I'll talk about some of these measures that people use a little bit later. I think that's a very, very important point. Yeah, I think, how many people are familiar with the shortest path problem? All right, like everybody, right? Okay, well that's good because that's a perfect example of a dynamic program. I was using it last night to find my restaurant, Google Maps, and the reason I can get an answer just like that is because these problems are very, very easy to solve and very fundamental. You can view every dynamic program, finite horizon problems, for example, at least, as a shortest path problem. Okay, it may not make sense, like the edges may not be time or distance, but could have some other meaning in terms of the edge weights on a graph, but very fundamental problem. So this is a problem I like to show in my first lecture on the course I teach on sequential decision making. The shortest path problem where we're trying to figure out the shortest path from S to G. Obviously, this is very simple. You can enumerate all the possibilities from S, but there's going to be a combinatorially large number of those, right? So working backwards through this problem, figuring out the shortest path from E to G, F to G, that's obviously trivial. The shortest path from C to G, is going to be that a choice between whether you go to E or F, and there's an immediate reward or cost, if you like, for that, and then the cost to go, the distance to go. So you're iteratively using the information that you're collecting over time to solve this problem until you get back to S. Okay, and so the whole reason that works is that in this case, like the state, which is the vertex, for example, and the actions are the edges that you're picking from. And the reason this works is because the state comprises all the information that you need to make an optimal decision. And this is fundamentally like the principle of optimality. And so this 1954 paper kind of described it as the property being that an optimal policy has the property that whatever the initial state and initial decision are, the remaining decisions have to constitute an optimal policy with regard to the first decision. So very simple, kind of conceptually, and then it's just been applied to an explosive, number of problems. If you think about it from a algorithmic perspective, there's different kinds of categories. This would fall into the, divide and conquer kind of approach. Okay. So more about terminology here. So I'm going to talk about states. In that example, it's vertices of the graph. Actions are which vertex to move to or which edge. There's a transfer function. That's a mapping from the current state in action to the next state. Okay, and then rewards. In this case, it's the cost associated with selecting an edge. And so the goal is to figure out the optimal path from S to G, and in the process of that, you figure out the optimal action to take in every state of the system. Okay. So I think that's 101. I'll just put a little bit of mathematics, more definitions around that. So if we have a dynamic program, I'll call the states S, I'm going to talk about finite horizon problems. Why finite horizon? I guess two reasons. One is that people don't live forever. Another one is that they're highly non-stationary problems in chronic diseases. Okay, things like the risk of a complication go up, rapidly, sometimes exponentially, as people age. So you can't really, a lot of the time, you can't really ignore that. You have to consider a non-stationary environment. So we'll have states, actions at a particular epoch. That'll be AT drawn from some set A, and then rewards. This is sometimes called the immediate reward that you get in epoch T. And then there's an optimal value function. And so this is a really key piece of information. You've got a function that represents the maximum total reward that you can get starting at epoch T and in state ST through the end of the horizon, where capital T is that last period. Okay? And that basically encodes the optimal policy. So if you know what that is, for example, if you know the optimal value function at T plus 1 for all the states you could end up in as T plus 1, you can pick that optimal action to get the value function. And so you solve this by recursion. So you start with a boundary condition, no actions here, that's the last period, so you're terminating at that point, and then solving this using backwards induction. And that transfer function I mentioned, it's not showing up here, but basically it's representing what the next state is, mapping that from the current state and current action. Okay, so that's just a basic deterministic dynamic program. And so it reveals a few assumptions I'm making. I said I'll do talk about finite horizons. I'm just going to keep it simple and talk about finite sets of decision epochs, actions, states. Okay, these are not terribly restrictive assumptions. We're talking about disease-related problems, but of course these could be relaxed, and they're not very restrictive, but they do keep things simple for the purposes of a tutorial. And then the decision maker's goal, I'm going to focus on problems where it's linear rewards, so you're adding them up over time, but there are lots of other approaches. You could look at like I said, like a probability of a bad event. You might want to minimize the risk of somebody having a heart attack, for example. So I'll stick with finite rewards, but just be aware there are all kinds of situations where you might want to extend beyond that. So I didn't talk about uncertainty yet, and chronic diseases are all about uncertainty. That's what makes decision making hard. And so there are a lot of ways that uncertainty arises in chronic diseases. So sometimes it's the health status of the patient or what the future health status will be in another year or 2 or 3 years. Okay, treatment effects. So a medication, the effect varies, right, depending on the individual patient. Diagnostic test results, procedure outcomes, all of these things could be uncertain. Okay, I'm going to give you some examples as we go through the tutorial. And so that kind of takes you into an extension to stochastic dynamic programs, or Markov decision processes would be the simplest version of that. So the optimality equations in this case, again, we have a state. It encodes all the information that we need to make decisions, finite horizon, that goes to capital T, but this is the last decision point. And then the optimality equations look just like what we had before, an immediate reward plus a future value to go, but instead of this deterministic transfer function, right, now we have probabilistic transfer. So we have transition probabilities. So if we're in a state ST and we take a certain action, the action can influence the probability we land in a future state, but it's probabilistic. Okay, if we took away the influence of the action, we wouldn't really have a problem at all. I mean, a patient might have a problem, but we wouldn't have any control over the problem. And so it's this sort of influence on induced stochastic process that is where the control comes from in these problems. Okay, if you want to get more into theory around this, I think, so when I teach this class, we start with examples. By the time we're done with examples. I think the students feel it's so intuitive, they're just totally bought into it. But if you want to formalize things, that you can do that. This is sort of a aggregation of a few different theorems in Marty Putterman's book that I use for my class. It's a reference book, and basically, this is a fundamental theorem that says the solution that you get from those optimality equations is going to generate the optimal policy for you. And the proof is very simple. I mean, it's by induction, as you might imagine. A lot of proofs are by induction when it comes to dynamic programming or stochastic dynamic programming, because you have this recursive kind of structure to the problem. So very, very easy to do to formalize it. So I'm not going to go through the proof, but you know where to find it. Wait, do you want me to go through 15 minutes on the proof of that? No? It's actually would be a lot shorter, but let's face it, it's, what time is it? 25 after 8 in the morning? Okay, I'll leave it to you. Yeah, a lot of people end up looking at special structured policies. If you're going to look at any kind of problem, I think it's important to understand what's going on, why is it going on, why is the data you're putting in leading to a certain policy. And so there's a lot of analysis that comes into play sometimes to understand what's happening. Makes it easier for explaining this to decision makers and probably implementing it. And sometimes you can exploit these properties to make it easier to solve, the problem. So for very large problems, that would be important. And so a classic thing would be like a control limit policy. So probably got a thermostat in the room here. So if we had states that represented temperature, for instance, then control limit policy would have S star representing wherever that thermostat is set. And if the temperature falls below that, A1 might represent turning on the heat, and A2 would be turning off the heat once we reach the desired temperature and go beyond. And I know if there are engineers like working on HVAC systems, they tell me that's not how it works at all. It's way more complicated, but you get the basic idea. Very simple. There's a threshold, and you switch your action depending on that. So you see a lot of problems like stopping time problems like that. And this is sort of a special case of a monotone policy. So control limit policy is one example. Policy is monotone if the decision rule, which is encodes the action that you would take at a particular time period for each state, is non-increasing or non-decreasing with respect to the system state. Okay, so this would be an example of that control limit policy. Maybe the state is like temperature. We have two actions. Once we hit that S star, our temperature that we desire, we switch off. So this action represents turning on the thermostat or the heat, and this one turning it off. Okay, and so there's some, yeah, please.
Brian, why are you saying control limit policy is a special case of monitoring policy? Do we have monitoring policy which are not control limit policy?
We do, yeah. So thank you. I didn't plant this question, but it's a very good one. And so, yeah, we could have that, right? So this would be another example. So we have states, maybe many actions, and we see this is like a non-decreasing monotone policy. So sometimes the action stays the same, but it's all going in the same direction. Okay, and so we do see that in other problems, simple problems where there's just two actions. Often you see like a control limit type policy. All of this, assumes, so what's going on here assumes that we've got some ordering of states, right, relative to our actions. So we have an ordering of actions, an ordering of states. Where does that come from? Well, it kind of comes from the nature of the problem, right? So for chronic diseases, the ordering might be states from low risk to high risk, for example. And the action might be, to start some kind of treatment, initiate medication, or have a procedure or something like that. Okay, and if we're looking at a more general case like this, then there could be lots of different treatments that could come into play. Okay, so in addition to sort of confirming often what you think should be happening with these problems, usually this is not a very surprise. It's surprising if you don't have some kind of structure like this for problems. But the more practical thing would be that you could use this structure to and the fact that you have a restricted set of actions each period to speed up, solving some of these problems. And this is important, I think, in some cases, but you can solve huge problems extremely quickly now. So a lot of the time you just kind of ignore that structure, and it's more about getting a deeper understanding of the problem as opposed to computational gain. If you want to learn more about that, this is another theorem from Marty Putterman's book. This is a general one that provides sufficient conditions for the existence of a monotone policy. And this is general, okay? So a lot of the proofs, analysis of these problems take advantage of special structure of the problem. Heart disease is not the same as cancer, it's not the same as diabetes. So looking at the problem can sometimes give you sufficient conditions that are more specific. But this is a generic. You could try it for any problem. It implies that you've got an ordering of states and an ordering of actions in mind, if you think about that graph I showed you. And properties are pretty straightforward on the reward function and the final period. The one that's not as straightforward is this property, which I'm not going to describe the mathematics about that. I'll just say basically what this represents. So the IFR property is the increasing failure rate property. And in words, it would say that the worse your health state, the more likely it is to get worse. Okay, so as you end up in worse health states, the probability of moving to a worse health state gets higher. And so this is a property on the transition probability matrix. It's very easy to verify. The question is, does it exist? Do you see this? And what fascinates me is every disease that I've worked on, we always find this increasing failure rate property. It's kind of a natural property of decaying systems. That sounds kind of morbid for decaying systems. Yeah, but there's treatment, right? And that's where the optimization comes in. So we always see this property. It's very, very interesting. And drives a lot of what the policies are going to look like, and drives also, whether you might have a monotone policy or not. Okay. So I want to give you an example. I haven't really given you any example of a healthcare problem yet. I'm going to show you a couple as we move through the tutorial. This one is one of the first problems I worked on, which is looking at if and when to initiate drug treatment, specifically statins, for controlling the risk of a heart attack or stroke in the future. How many of you have heard of statins? Okay, I'm not going to ask if you're on them because that'd probably be a HIPAA violation or something, but a lot of you haven't, but it's kind of like a wonder drug. I mean, people have gone as far as to say maybe we should put it in the water system. They're very effective at lowering risk. Some people would advocate that everybody should be on one, but because there's uncertainty about long-term outcomes, typically you wouldn't go on one unless you were at risk of heart attack or stroke. And so there's a lot of them. So some of you are under maybe 30, but the rest of you know that we used to watch shows on TV, not on a computer, and there were these things called commercials. And commercials, there was 1 million of them for all these different statin drugs. There's one I loved with somebody paddling a canoe, and they're fantastic. And then at the end they would say, oh, by the way, there's some side effects, like a rare chance your head will explode or something like that. But actually the side effects are moderate, but not zero. Some people experience side effects that could be muscle pain, nausea, whole range of things. So this is a problem where we looked at whether to initiate statins or defer initiation on the basis of what's going on with the patient's health. Okay, so more about that. So we looked at this problem starting at with a time horizon of age 40 to 80. Annual decision epoch, so you could think of it as you're going to see your primary care doctor and getting a cholesterol test every year. And you have a decision to make. So the action is either to initiate statins, and I'm calling this Q for quit. Okay, initiate sounds like start. Okay, but I'm calling it Q because it's sort of a stopping time problem, and you can think of it as you're stopping the process of not being on statins. Okay, so this is a problem that falls into the category of stopping time problems, where you're sequentially making decisions and then trying to decide, do you want to take that decision or avoid it? Avoiding it would be delay. C means like continue, without statin treatment. And then risk factors are total cholesterol. Okay, if you ever had a cholesterol test, you've seen this. Total cholesterol, you can think of that as bad cholesterol. HDL is good cholesterol. And these are biomarkers, that are commonly used. And so then demographic things that would be like static over the course of the horizon would be things like, race, BMI, smoking status, other things that are important predictors and go into risk models that predict heart disease risk. So I'm going to turn that off. So this is, here are the optimality equations again, but a slightly simpler structure. Here, we're deciding between two different actions, whether to start statins or not. There's a reward. You can think of that as the long-term reward if you start statins. Okay, so that reward might represent your quality-adjusted lifespan, expected quality-adjusted lifespan, if you initiate treatment. Okay, if you don't initiate treatment, you get some immediate reward. It could be the year of life that you just experienced without having a heart attack or stroke, but then there's a future reward to go. Okay, so a probabilistic transition, and then at the next period you're faced with that same decision. Do you want to start statins or not? And so the reward would be time dependent, because survival varies obviously in terms of age. If you're very young, you've got a higher expected survival time. For example, if you're older, that time is shorter. And this actually plays a lot into the structure of the policies that you get when you solve these kinds of problems. So if you like pictures, here's an example. So this Markov chain, there's a couple of risk factors. Maybe you just think of this as like total cholesterol. So if it's low, that's good. Medium, high, very high, that would be a high risk state. And people transition through this, and you can see the dynamics of how they transition by looking at longitudinal data from electronic medical records. So these transitions are occurring, and there's some probability, that the individual would have a heart attack or a stroke. That's something you can estimate from a risk model. Okay, there are a number of risk models out there. Frequently, they're like survival models would be the basic kind of model that can estimate the probability of an event based on risk factors, like the demographic ones like gender or smoking status, but also on the basis of cholesterol levels. And then there's a decision. You could start statins, and since it's a stopping time problem, we can think of that as like a single state that you enter. Of course, the dynamics are still going on, so this is a simplification of what is really like a separate Markov reward chain. We're assuming there's no decisions. We're just focused on the statin decision here, but it's a separate Markov reward chain with a reward that corresponds to the expected survival for someone who's initiated statins. Okay. Is that clear? Are there any questions at this point? Okay. It's great, and people are still awake. It's going well. I'm gonna keep talking until everybody falls asleep. So I'm just kidding. I'm not going to do that. I'm definitely going to finish on time, and hopefully before on time. So in terms of rewards, there's a lot of different ways you could look at this. Like we talked about, cost. So there's a cost to statins. Used to be substantial. Could be like $1,500 a year, for example, for brand statins. Now they're generic statins. So the picture's changed a lot. Very, very cheap, but not free. The first work that we did was to look at a simple model that just ignores cost. Okay, so we'd say that's like the patient perspective, assuming the patient is insured. Okay, I'm not going to go down into that. I'm not going to turn this into a political talk, but with if people have insurance and have access to it, they may care only about their quality of life, length of life, but also quality of life. And so the simplest thing would be to say that the immediate reward is just the time between decision epochs. So if it's annual, pick up a year. For every year you haven't had an event, and and then RTFS is the expected future life years, but adjusted for quality of life on medication. And so what do I mean by that? Well, health services researchers, for example, do a lot of work to try to study impact on quality of life. Sometimes they would express it as an estimate of disutility, so like a numeric estimate that would represent, you can think of it as a penalty term for being on statins. So they'll ask patients questions, or a lot of approaches for this. There's standardized surveys to get estimates of what the patient perspective is on the impact of initiating a medication. Okay, and for a medication, it's very low. For a major surgery, it might be quite a bit higher, for example. And it's also something that's relevant to having a major event. So people who have heart attacks and survive, they rate their quality of life to be, it varies, but between 0.8 and 0.9 of a perfect year of life. Okay, so they're largely because they're not able to eat some of the same foods they would have liked to, do some of the same activities that they would have liked to, and so on. So that's survey collected data, and a lot of that's in the literature. So that's not the kind of research I do, but I work with people that do that kind of research, and it can be an important input to these models.
It's trying to compare apples to apples, basically.
Yeah, in what sense?
You're going to say, if I have 30 years to take these medications and I'm only going to get a year out of it, then it might not be worth it. But if I'm going to get 2 years out of it, it will be worth it.
Yeah, you're basically making that trade-off, right? Trading off the immediate risk of something bad happening with the potential long-term gain that you would get, but adjusted for the impact of starting that treatment. Yeah, so this is a classic stopping time problem.
The function is so personal.
Yeah, absolutely.
I don't see how you would solve it generally.
Well, what you can.
One-on-one treatment.
Yeah, so what you can do is, and there's a lot of effort to work on decision aids to help patients sort through what's best for them. If you have a financial portfolio, you do this kind of thing all the time, and it tends to be you're given different options, like, would you be happier with scenario 1, where you're on statins, and your risk of heart attack is lower, or scenario 2, where you're not and you're carrying along a larger risk. I'm kind of making it up that. It's more complicated than that, but basically the idea is you get given a series of scenarios that help to determine what your personal risk would be. Nobody has done this for a lot of the cardiovascular disease drugs that I'm aware of, but there is work going on to look at procedure things. So I'm working with somebody who specializes in this kind of work to look at what is the disutility associated with like a biopsy, for example, for prostate cancer.
These are averaged over populations. So,
yeah, so these estimates that we're using are averaged over populations, but personalizing it.
Some people, you can tell them risk, minimize your risk of heart attack, just do more sports.
Yeah.
Eating cheeseburgers. People don't do it.
Yeah, well, yeah, exactly. Yeah, I mean,
policy.
behavior, like diet, exercise, those have much more impact than statins, but the catch is that they're not effective. People aren't very good at changing their behavior, actually. So, so actually, I think that's one of the big frontiers is like what are the behavioral impacts of what's going on, and how do you understand that? This is a very simple model for a complex decision that a human being is actually making on their own.
Could you talk a little bit about solving this problem for certain subsets of the population? Maybe that might help.
Yeah, absolutely. Yeah, so, actually that's a perfect segue, and then we'll come back to it if you don't feel like I answered that question. But so I'll talk about computing transition probabilities that underlie the Markov decision process. This usually involves, so in this case, we're talking about like total cholesterol, HDL, I'll call those metabolic health states. We use longitudinal electronic medical record data for large numbers of patients, so using population data to try to estimate transitions between these states. And then in terms of complication states, there are published risk models for estimating the risk of an event. In this case, a very popular one is the United Kingdom prospective diabetes study. This is because we were studying a population of patients that have diabetes, so they're at higher risk of cardiovascular events. There's also a model called the Framingham model. Okay, that's based on a very well-known study in Framingham, Massachusetts, started in the 1970s. Which model's right? Okay, well, it depends who you ask. Your doctor might be looking at Framingham, and your doctor might be looking at UKPDS, and there's more models emerging. And so there's ambiguity in those cases, and I'm going to try to talk a little bit about how you address some of that a little bit later. Yeah.
Do you discount the report over the length of the time horizon that you're looking at?
Yeah, we do not, but there's a lot of debate about whether you should be doing that or not, whether you should be discounting future years of life. There's actually evidence to support that would be a rational thing to do. We did not do that in this case. It's sort of controversial to some extent, but it would not be an unreasonable thing to do, and that's an argument you could support. And some people would say you're wrong, and some people would say you're right. Yeah, so great question. So how do you estimate the transition probabilities? I guess the simplest possible way would be to look at longitudinal data. So this is data, totally anonymized. This one is for male patients because we looked at males because they have very different risk dynamics compared to females when it comes to cardiovascular disease. And so on the y-axis, we've got total cholesterol levels for a cohort of patients, around 500 patients, and then age on the x-axis. And so what we did is take this continuous measure and break it up into 3 groups: low cholesterol, medium cholesterol, high cholesterol. So we're discretizing the state space and approximating things with that discrete set of states. And then linking records for a patient. So this is a patient that had low cholesterol, a couple years later ended up with very high cholesterol, and then it went down, lower cholesterol, and they're bouncing around. Okay, and so we can get estimates of these transition probabilities by looking at that data. The simplest way to do that is to look at the proportion of transitions that are happening from time period to time period. Okay, so basically to do that, you're counting, okay, the number of transitions from one state to another divided by the total number of transitions from that original state, and that gives you a statistical estimate. What you need to be able to do that is laboratory data. So that's the cholesterol data, the data that's coming back from a lab after a cholesterol test. If you were wanting to include other things like blood pressure, and so we've studied other risk factors, so clinical data is important. So that's coming from a totally different source, right? It's like the blood pressure cuff that your doctor's putting on you. Doesn't seem like a big deal, but when you want to try to fuse all this data together, that's where it starts to get very, very complicated. But it's becoming much less complicated now. In recent years, it's incredible some of the things that are becoming possible. And then pharmacy claims data. So the thing I skipped over is, why did this cholesterol go down? Maybe they got their diet back in order. Maybe they started statins, right? And so we have to have some idea of what's going on. Pharmacy claims data tell us somebody initiating treatment. Okay, so we can see whether they got a prescription and whether they filled it. We can also see if they're filling it over time. Okay, so a lot of people actually drop off of statins. They stop taking them. And that's something that's actually not clear why that's happening. And so that would be a factor that would influence those transition probabilities. So to get back to the idea of like different groups, so this is based on a study for patients with type 2 diabetes. We looked at men and women because the dynamics of cardiovascular risk are very different. It's not that women aren't at risk, it's just that the onset of risk happens a little bit later in life, and for many. And so this is a lookup table or an optimal policy that you're looking at here, in this case for women. And we've got states that represent total cholesterol, bad cholesterol, and then good cholesterol. And there's not a perfect ordering here. There's a partial ordering, okay? But so, roughly speaking, we're going from high risk down to low risk, okay? But because there are these 2 different dimensions to it, it's not not a complete ordering. But what you see is basically, so red means don't start statins, green means start statins. You know, at around age 50, somebody who has very high bad cholesterol and low good cholesterol would be recommended to initiate statins. As you get old, as a patient gets older, there's more initiation. But if the cholesterol is kept under control, you know, women might avoid entirely starting statins. Again, this is for patients with type 2 diabetes that are at heightened risk. And so then over time, we see a decrease. What's going on here? Well, what's going on is that the benefits of initiating treatment at older ages start to go down. And that's because there are these competing risks that exist. So as your other cause mortality risk goes up, the other things that could cause you to die. Okay, I'm still a bummer. I guess it's too early for that kind of talk. But it starts. Other risks start to play a more important role, and so we see less benefit, and there's a natural drop off where you're not putting people on statins at age 80. For men, different story. Cardiovascular risk comes in, and basically the recommendation is that all men would start statins at some point in time. So very different. The different populations have different risk profiles, for example. This is not exactly personalized medicine, it's just separating men and women, but it's sort of surprising how little personalization has occurred in medicine. There's sort of this dream that everybody will have their own personalized profile for what to do based on genetics. That might happen someday, but even things like this, so the reason we looked at this was because there really wasn't any separation of what to do for men versus women, even though the cardiovascular risk dynamics are very different.
You look at the option of stopping?
We did not, and the reason we did not is, and that's a great question, when you start statins, the intent is to start them and stay on them. We don't really know what happens if you just drop off them. Yeah, I'm sorry?
Drug manufacturer's intent, but medically speaking, what is it?
Yeah, medically speaking, that's the intent too. So your doctor's not going to say, "Oh, we'll take you off statins," because we don't really know much about what would happen. So it's you can think of it as an irreversible decision, but there are always special cases. And one is that statins can cause problems with your liver. It's very rare, but they'll do some tests on your liver function shortly after starting. And if you're showing signs that there's harm to your liver, then that would be a situation where you would stop because it's medically necessary. Yeah.
So here you focus on the policy on initialization decision.
Yeah.
I imagine there might be some situation where the dosage of the treatment may matter.
Yeah.
Along the way, right?
Absolutely. Yeah. So the way we looked at this is a great question. The way we looked at this is, and when I say we, so this was work that was done with somebody with a pharmacy background, somebody who is an endocrinologist that does research and treats patients with diabetes. The feeling was we'd choose like a nominal dose, and so the data that we got was basically binary. You're on statins or not, but depending on your weight, for example, you would potentially start a dose that varies. There's not a huge variation in dose, but now actually what's happening is people are looking at it as multiple treatments. You start low dose statin, see how it goes, then you might start a high dose if your risks continue to be high. That's a much more recent development.
Yeah, but that expands the action space.
Yeah, exactly. Yeah. Exactly. And so in terms of other work that's been done, so that's a very early paper. That's the first thing I did to get into medical decision making, first project. There's lots more to do. I'll, at the risk of embarrassing Jennifer Mason back there. So more recent work involved looking at multiple treatments for cholesterol and also blood pressure. Cholesterol and blood pressure, they get treated separately actually when you look at the guidelines, medical guidelines, but that doesn't really make a whole lot of sense when it comes to cardiovascular disease, because they can both influence those outcomes of whether you're going to have a heart attack or stroke. And so looking at them together, and something that Jennifer did as part of her work was to look at what are the benefits of pooling the decision making versus using national guidelines, which would say keep them separate, cholesterol and blood pressure. And there appears to be a lot of gain, and that's something that's getting traction now. Maybe you should use risk to decide how to treat, and not just cholesterol or blood pressure. People don't care about cholesterol or blood pressure. What they care about is not having heart attack or a stroke. And so it's a very logical argument, but there wasn't a whole lot of data to support that. So if you're interested, I would check out that paper. Moving along, so I'm talking about stuff that I've done because that's the easiest thing, frankly, but there's a huge amount of work out there. I could not possibly review all these things in a 90-minute session. I just give you a few examples of papers I think are great to start with, on like liver disease, kidney disease, ophthalmology, dementia, all kinds of interesting work out there, much broader than this. So, and again, these slides are up on my website, so you can grab these. These are a couple of books I like. There's a lot of books out there. These are just a couple that I've found useful. Marty Putterman's book on Markov decision processes, and then Bert Zekas' book on dynamic programming. But there are a lot of other references out there. These would be good starting points, though. So that's MDPs. Okay, now I'm going to move on, unless there's any questions. Are there any questions about that piece? What's that? Check it off. Okay. Yeah, that's the kind of sort of the foundation you need to start to get into other topics. So I'm going to talk about partially observable MDPs. Fewer of you are as familiar with those. So partially observable MDP, the idea is that you can't see the underlying state directly. So a lot of things are in terms of definition, are the same as for an MDP. Sometimes people call the states core states or unobservable states. So it could be like a health status of a patient. They might have cancer, for example, but it's not been detected, and without doing something like a procedure or imaging, you can't see it. Okay, so these things are all really same as the MDP. With POMDPs, then you introduce observations. The observation might be like a biomarker result, an imaging result, and then there's an observation probability matrix. So the observations themselves are probabilistic. Okay, so if you have two different states, you have two different distributions. Both could have false positives and false negatives associated with them, and so there's this uncertainty that exists, which makes this a complicated problem. It's not like it's a litmus test that says this patient has cancer and this patient doesn't. There's a lot of uncertainty that's encoded in the observation probability matrix. And so the way you could think about this conceptually is there's some starting point with some belief. The patient is in a certain state, so we'd call that a belief vector. It's got a number of elements that's equal to the number of unobservable states. And each element represents a probability that the patient's in a particular state. So the elements of the vector sum up to 1. Okay, and then there's updating of the vector, an action that gets chosen. It's not based on the state, because we don't know what that is. It's based on the belief vector. Now, the probabilistic distribution of the states the patient might be in. There's a transition that occurs. Of course, this is unobserved, but there's a transition according to a transition probability matrix. There's an observation that's received, so that could be one or more biomarkers, test results that provide some information, and then a reward. And then based on that observation and the prior belief, you do a Bayesian update, end up with a new belief, and so on. And continuing until you reach end of the horizon, if it's a finite horizon problem, with some reward that's, again, just like an MDP, depends only on the final state. And actually, this should be the belief. Could only really depend on the final belief and not the true underlying state. Okay, so that's the kind of basic process for partially observable MDPs. And the belief vector that I just talked about is a sufficient statistic for POMDPs, meaning it encodes all the information you need to make decisions, okay, to make an optimal decision. And so what does this belief represent? So this is one element of that belief vector. So that would be the probability that the patient is in state ST, and that's the can be expressed as the probability of being in ST given the entire history of what's happened. So all those actions, all those observations over time. So it depends on the history. I'll call it HT. This is a sufficient statistic, but an awfully complicated one, right? Because it's involving this entire history. But the nice thing is that you can, and I think I won't kind of go through all the details of this, but you can check this out. Basically, you can use Bayes' law, okay, and reorganize the numerator and the denominator. And what happens is you can re-express it in terms of prior belief. And the only place that the history now pops up is in this term here. And we find that same term in the denominator. Again, the rest of it only depends on the prior belief. And so for belief updating, what you get is a dependence only on the prior belief. Okay, and then the most recent state and observation. Okay, so there's that history dependence is disappearing, and as you're doing this Bayesian updating over time, you're avoiding having to deal with the entire history. Okay, so this is making it sort of more tractable in some sense.
It's become Markovian.
I'm sorry?
It's become
Markovian, exactly. Yeah, thank you.
Isn't that called Bayesian chain rule on the Bayesian belief network structures?
Yeah, it is. It's not. Yeah.
It's a different name on this.
Exactly. Yeah, this is more like literature on partially observable MDPs, but I'm sure that that sounds right.
Bayesian belief.
Yeah, exactly. So it's sort of simplifying a lot of the structure. So again, we have rewards, like immediate rewards that are obtained, and what else? And then optimality equations that look somewhat similar. Okay, so the reward could be expectation over, related to the state transitions. And then the optimality equations would be, in some ways, similar. Now it's not ST, not the underlying state, it's the belief state. You're choosing actions to maximize an immediate reward, but it depends on the particular, it's an expectation over the belief now. And then there's a future value to go. Okay, and so how do we breaking down this a little bit, the probability of, so this represents not the transition from one state to another, but the probability of an observation OT plus 1 given the belief vector BT, okay, so that current state and action AT. And then this represents the updated belief given that observation OT plus 1 and then the action that was taken. This is sort of, so this becomes like a, once you look at it this way, it's a continuous Markov decision process, similar to anything. There's not really anything that's not observable here if you accept that things are premised on the belief state. Yeah.
This might be a stupid question, but then when we look at the rewards, it actually it involves the conditional probability of the state, but which usually are not observable because, and then how to actually estimate that, because in reality, if that's not observable,
Yeah.
and the state is not observable, but then condition on the previous state and the action you can just, that's known, but
Right.
the states are not.
Yeah, so that's why we're taking the expectation with respect to the observation conditional on that state. So this is a yeah.
The term in the middle, usually how is that? How can someone estimate it? I mean, in the between in the reward expression. So this one, yes.
Yeah.
P of ST plus 1 condition on ST, comma, AT.
Yeah, exactly. So we're taking the expectation, and then with respect to the observation conditional on ST plus 1. So it's a expected reward. We don't really know exactly what the state of the system is, so we have to take that expectation over the belief down here. So it's presumed that if we knew what those states were, we can compute that. We don't know exactly what it is, so then we're taking the expectation. So that's a dot product where all these elements represent the probability of being in each one of the states.
The question might be that how do you estimate that from data, for example? You can to learn the P?
Yeah, great question. So I'm going to come back to that. I think that's a really fundamental question. And so, okay, so I'll skip ahead a little bit on some things because there's a couple topics I want to hit. But I don't want you to stop asking questions because that's what we're here for, and there's a tutorial you can read whenever. These problems are hard. They fall in a complexity class. They're p-space hard, so there's no polynomial time algorithms. If you're not into complexity theory, you could think of this as being like the class of like NP hard problems. So we're not expecting this to be a tractable problem that we can solve. Yes, yeah. I mean, p-space is, so there are all kinds of interesting questions around it, like the MP problems are in it, but is it a strict subset of p-space problems and all that? I think from a tutorial perspective, they're hard, and they really are extremely hard problems to solve. So even very small problems are shockingly difficult to solve.
It's so excited about formulating it this way because it makes a lot of sense until you have solved it.
Yeah.
Then all of your enthusiasm dies down.
Yeah, exactly. I have this all the time.
Why did I do this?
Students go try to solve it, and then they're like, it's working, but it just keeps running and running and running forever. There are all kinds of, the key thing is there's all kinds of approximations, like discretizing the belief space from continuous to finite, for example. That's one approach. There's a lot of structure to take advantage of here. So maybe you can see this. If we were, at the boundary condition, for example, we've got a value function, because we're taking that expectation, it's a linear function of the belief. And the procedure that you're doing as you work backwards through this problem is essentially constructing linear functions, so piecewise linear functions that represent supporting hyperplanes. So the important piece of structure is that the optimal value function is piecewise linear convex, okay? And so it's based on a set of supporting hyperplanes, and some things that people do are take advantage of that structure, like just sampling some of the supporting hyperplanes. So a very small number could be enough to get a very good representation of the optimal value function to solve the problem. Yeah?
It's similar to the classic MDPs where you leverage monotone policies in the state space. Has there been much work done on leveraging monotone policies in the belief state?
Yeah, that's a great question. So as far as I know, not a whole lot. We tried to leverage it on some problems. I can't remember why, but it starts to become very difficult, partly because of the connection to Bayesian updating. So I think it may be that there are those opportunities there. Certainly, if you're in some context like infinite horizon problems, for example, where you don't have this non-stationary dependence, and if you knew there was a control limit policy, then that could be a very useful piece of information. Proving like structure, like monotone policies, is a lot more complicated for partially observable MDPs than for regular MDPs, but there are sufficient conditions out there, and they rely on things like IFR property, but also other properties to try to prove that. So I don't have a great answer, but my sense is that there's not a whole lot. If anybody has any ideas? Okay, all right. Well, I feel better if nobody knows. Yeah, but I think the answer is no. So here's a quick example of a problem with in prostate cancer. This is a screening problem. So PSA is a biomarker that you get. If it's high, that could be bad. If it's low, that could be good. But sometimes people have high PSA and they don't have prostate cancer. Sometimes people have low PSA and they do. So there are these false positives and false negatives. But there's information there. PSA tests are just blood tests, very simple. Cost about $35, practically nothing, but lots of problems with them because they don't there are high false positive and false negative rates associated with them. That might be used to decide whether to do a biopsy. That's more invasive. Then it's basically like an outpatient procedure, painful. A pathologist looks at the results and then evaluates them, uses a scoring system to score the cancer. So there are a lot of different kinds of prostate cancer. Most cancers are like that. Some are very low risk, some are very, very high risk. Now if it's positive, you might go for treatment. That could be like radical prostatectomy, surgery, or radiation therapy would be another, those fall in the category of like what would be referred to as definitive treatments, so or curative intent treatments. And then if there's no biopsy triggered from PSA, then do a PSA test. And so PSA as a biomarker, this is just a quick simulation that shows for some hypothetical patient. It's not just, I didn't just sample this once, I tried to pick something that looked nice for a presentation, but this is intended to give you an idea of what's going on here. So we have a patient that, according to the underlying Markov chain, moved from the no cancer state to the cancer state at this point at age 52. And there's one that continues cancer-free, same patient, one that has cancer, and their PSA evolves differently. So having cancer means your PSA tends to increase, but there's a lot of uncertainty. So medical doctors debate about what's the right threshold. There's an enormous debate about whether even to use PSA. The most common would be a threshold of 4 nanograms per milliliter of this biomarker in your bloodstream. If you use that as the threshold to biopsy, you're going to catch this patient at around age, I guess, 62 or so. So about 10 years after they developed cancer. So why not lower it? That's what lots of people say. You lower it, and next thing you know, you're catching it 5 years earlier. Okay, so this is great. You keep lowering it. 2.5 is another threshold that people advocate for. People, by that I mean urologists. But then you start to get into having biopsies for people that aren't going to benefit from them. And it's a major procedure, and so that harm has created huge national debate, still raging, about whether you should even use PSA at all. So in terms of this model, so we have core states. This is the simplest possible model where we have a binary model. Patient doesn't have cancer, or they do have cancer. Okay, so this is one of the first problems we've my group worked on, and then from the cancer state, it could progress to metastatic cancer, and then a patient could die from cancer or from other causes. So I'm not showing all the lines here. On the left side, I'm going to move over to the right, point out that patients who are treated, so that present treatment, and the outcome could be that the cancer is organ confined. It could be extraprostatic, meaning it's extended beyond the prostate, or lymph node positive, meaning that it's metastasized. Okay, so these are 3 different outcomes, and we didn't look at decision making in these stages. We're focused on the screening problem and differentiating patients with and without cancer to decide whether to get them treatment. So these treatment states can be consolidated into a single one. And then so I'm adding back in the dotted lines that could just have well been here if there weren't caused too many lines. But patients can die of other causes. Okay, heart attack, stroke, any number of possibilities. And so one of the big things with prostate cancer is that other cause mortality plays a huge role. So there are a lot of prostate cancers, low-grade ones, that are best left completely undetected. Okay, actually, the majority of men die with prostate cancer without even knowing they had it. I hope that doesn't freak everybody out here, but not everybody. It's not an equal opportunity disease, so just the guys. So that plays an important role, and then this is just a 2-state partially observable MDP to solve. So I think you had a question, right?
Just clarification. State M stands for what?
Yeah, so it stands for metastatic cancer. So so somebody could have cancer that is confined, and then but it could metastasize. And this is a great question because I didn't say this. This is a completely observable state. So we assume that at this stage, the symptoms are significant enough that a patient is going to see their doctor. And those are things like they might have back pain because they had a bone tumor. Okay, that's a very common place for cancer to spread for prostate cancer. And so our goal is to try to keep people out of this state because they rapidly move to, the survival is not good for people with metastatic cancer, but it's getting, actually there's some incredible things going on with immunology and immunotherapy. Okay, so I'll have to pick a couple things I want to talk about. I want to say a few words about how you, I think I'll focus actually on the rewards here. So there's a lot that goes into estimating the transition probability matrix. I'm going to say more about that in a minute. In terms of quality, in terms of what the rewards are, so we looked at quality adjusted lifespan in this context. And so we have rewards. The rewards differ depending on if the patient is in the no cancer state or the cancer state. So no cancer with no PSA test would have a reward of 1 representing perfect health. PSA test has a very small disutility associated with it. When you look at that, not so much the blood test, but some of the anxiety that potentially comes from having that test. And then biopsy has a much higher disutility. This is a painful outpatient procedure and has a low but not zero risk of a serious infection occurring. And then for patients in the cancer state, if they're in the cancer state but it hasn't metastasized, we assume that there's no symptoms there. Okay, so they're living with perfect quality of life. If they have a PSA test, again, there's that disutility. If they have a biopsy, it's a little different than the patient without cancer. Patients with cancer, they have a biopsy. There's the disutility of the biopsy itself. And then, in this case, we're assuming that they're going to get treated if they're detected with cancer. Okay, so epsilon is the disutility associated with treatment via prostatectomy, and F is the biopsy sensitivity. Okay, so about 80% of the time, if there's a cancer present, then it's detected by biopsy. Why not 100% of the time? Well, biopsies are sampling, usually like 12 samples from the prostate. Sometimes they miss the cancer. So it's not a perfect test. And so if you want to learn more about like where all that stuff comes from, like these mysterious disutilities, and how you estimate quality adjusted life years, this is a great classic reference. There are a lot of other references out there, but this is sort of a very classic one. I encourage you to read it, and again, the slides are up on the website, so you can grab that. It's actually kind of fascinating. I don't know who was first. We'll go over here and then we'll come back. Yeah. Did you have another question?
We expect epsilon greater than mu, maybe.
Yeah, much larger.
Than the delta.
Yes. So delta, extremely small, like 0.001. I can't remember exactly. Disutilities for biopsy, we estimate at 0.05. That's based on a study from a cardiovascular study that looked at people that were having, what do you call it? Suddenly I'm blanking on the term, but having a diagnostic procedure where they run angiogram. Yeah. Okay, so why do we do that? Why would we use that? Because nobody had done this study. So there's a project going on now at Michigan, led by somebody else, but I'm involved in it, where they're estimating disutilities associated with biopsy itself. And it's something that's very important, and a huge gap in the literature, I think, is that we don't have good estimates of the impact, the harms from treatment. Okay, everything's kind of geared towards what are the benefits of treatment. Pharmaceutical companies, they're completely incented towards the benefits of treatment, and studying the harms, doesn't happen as much. Not because I think people wake up and say let's hide or do something nefarious. It's more like there's not that incentive, and so there's not incentive to spend a lot of money on doing those kinds of studies. So I think that's really actually incredibly important. I know you had a question.
Clarification question. So after PSA test, if it's positive, then we always do biopsy.
initiate treatment right after PSA test.
Yeah, yeah. But if so, in this context, so in this context, that's what would happen. But in the context of using a partially observable MDP, what we would be doing is solving the optimality equations, and instead of making decisions based on PSA, which is just the surrogate measure of risk, you're making it based on your estimate of the risk that the patient has prostate cancer. And so over time, you're using all of those PSA measurements to update that risk and making decisions based on risk instead of this biomarker. And so you can get a lot of benefit from that. A lot of the controversy around PSA is, some of it is there because it's not being used all that well. You're only using a single value as opposed to the history of values that you could use to estimate risk. So thanks for pointing that out. Let's see, we used model data, in this case from Mayo Clinic. I show you this to point out, there's an enormous amount of bias here. So we use longitudinal data from a study at Mayo Clinic. Mayo Clinic is in Minnesota. A lot of the people that are served there are and Arizona. Yeah, great. So this was from Rochester, Mother Mayo, as they call it. Thank you for correcting that. And it's the population was it's all men. Okay, well that's not a problem in this case because women don't get prostate cancer, but 96% Caucasian. So it's extremely important to represent. All data is biased, and if you're not really understanding the population that you're working from, the recommendations that are coming out of your model, they may not apply to a certain population. So this is something I think it's incredibly important. Biostatisticians think about this constantly. In my experience, like in the OR community, we don't think about it as much. And so I think it's incredibly important if you care about the answers. And if you're going to work on problems where you want to learn something about chronic diseases, then presumably you care about the answers that you're getting. So we're lucky to have access to other data sets now, a lot more. But I wanted to acknowledge that. That was one of our first studies. So here's what the optimal solution looked like for this problem. This is the paper if you want to learn more. It sort of indicates where we were able to prove some things about threshold policies in this case. Numerically, you see there's a threshold type policy. So what I'm showing you is age versus the probability of having prostate cancer. So that's that one belief vector element for prostate cancer. And so DB means do a PSA test, but don't do biopsy. And so the recommendation is, do PSA tests. Always do PSA tests. And a lot of medical doctors, if you're not familiar with the idea of Bayesian updating, learning, partially observable MDPs, they would say, well, that's crazy because every time you do a PSA test, there's a chance it'll be a false positive and somebody will get a biopsy. But that's not the case if you're trying to learn from that data. If it gets a bit higher, a higher risk, then the recommendation would be to biopsy. And then what you see happening here with this jump is other cause mortality starting to kick in. Cardiovascular disease, other kinds of mortality, to the point where eventually it's recommended that you would stop doing any kind of screening for prostate cancer. And this was at about age 76, which is remarkably close to a recommendation from a panel of urologists formed by the American Urology Association that recommends stopping at age 75. So, so smart, urologists that really understand the disease, coming up with sort of the same thing that we did, where we have tried to make use of the data. So it's I think it helps to confirm, some of these things. Other examples, way too many to mention. These are some great starting points, like work on breast cancer by Lisa Mailer, Julie Ivey and company. Really interesting work on colorectal cancer. C, is C still here? Yeah, okay. So not to embarrass you, but really interesting work on tuberculosis, heart disease, and there's a lot more out there. Okay. One thing I want to make sure I don't forget, though, is that it's like the tip of the iceberg. There's so many diseases, there's so many problems that haven't even been studied at all, from I mean, not that they're not studied, but OR people haven't tried to look at them and try to use methods like optimization. Doesn't have to be MDPs or whatever, but for like, people that are looking for new directions, you could still become the OR expert on thyroid cancer or like any number of things that really haven't been delved into. So I think we're at a really exciting time. I think in 30 years, people are going to be saying, oh, you all had it easy because there are all these great problems, and now, everyone's, they've all been tackled. So take advantage of that, because it's just like an enormous number of open questions.
Doctors keep changing the problems over time too, so I don't think that'll ever happen.
Yeah, and new technology coming in, new imaging technology. I mean, it's just things that change so fast. It's incredible, and the availability of data now is just opening up so many opportunities for us. So, if you want to learn more, so again, the slides are up there. Check it out. I love this tutorial. MDPs for dummies. The person who created this is super smart because it's not really for dummies. It starts from the beginning, so it's a great resource. And these are some other papers.
Code there, right? An algorithm.
Yeah, code on all kinds.
Very well. You have to code your own algorithm, right? Would you agree with that?
Yeah, I actually haven't used those algorithms, but there's a lot of description of different approaches. It's a great first stop to learn more. And these are other papers, some seminal, some more recent, like review papers I've found useful if you're looking for a starting point. Okay, let's see. Can everybody hang out for another hour and a half? Probably not, right? Okay, well, this is good. We had lots of questions, so that's what I wanted. Slides are up there. The tutorial exists. Maybe I'll just leave you with one last thing. So how many of you have heard of the Movember Foundation? Yeah. Wow, not that many people. Okay, so it's a group tries to promote understanding of men's health issues. One thing they do is it's called Movember. So November is the month where you grow a mustache and try to raise money. And so for people that don't like mustaches or have wives that don't like mustaches like me, it's kind of a big investment. So this is me rocking a pretty amazing biker mustache. Yeah, that took me a while to build up. And then the reason I did it is because our grad students came up with this idea of doing it. They started growing beards, and I did research in prostate cancer, and I thought, well, I have to do this too. And so that's a whole group of us. And for people that couldn't grow beards, there were materials that you could create your own, they call them FOMOs, so fake mustaches, and those are pretty awesome too. So, but we're working with data, so that's from a very large number of studies. Movember put together this data set. They convinced 25 established active surveillance cohort studies to pool their data, and so we're working with that now. It's opening up all kinds of opportunities. So fortunately, there's another talk at this conference where you can learn about how to parameterize some of these models. You basically using like a EM algorithm or like maximum likelihood estimation techniques to parameterize models where, what we don't have is, so these are unobservable states. This is for people on active surveillance. So low risk cancer is, deemed to be okay. High risk cancer is something that needs to be treated. With active surveillance, you're monitoring it over time. But you can't see these states. What you can see are things like biopsy results and PSA levels and that sort of thing. You can learn using an EM type algorithm that essentially involves, so Baum-Welch is one type of algorithm. It uses dynamic programming actually to estimate a model that's most consistent with what you're observing. So it's just doing maximum likelihood estimation, but in the context of having certain only observations from which to estimate the model. And if you want to learn more about that, this is a fantastic tutorial. I really highly recommend it. It's in the context of speech recognition, but it's very general. They just use that as a motivating example. Very easy to read and very comprehensive. I think it's just a fantastic tutorial. And so I'm not going to have time to talk about all this stuff, but fortunately, there is somebody that will talk about it. So Wei Yu Li is a PhD student working with me. And he's giving a talk on the whole process of using this observational data to directly estimate a natural history model from that data, and then optimize, so solving the partially observable MDP to find optimal treatment decisions. And so that's, you can find that in the program. It's TD76 tomorrow. There we go. So we got through a few things, and I think I'm going to skip over this stuff on robust MDPs, which is a really exciting area. Lots happening to study problems from the perspective of uncertainty, in the data that you use to construct these models, because they're all statistical estimates, right? So ignoring that doesn't make a whole lot of sense. And there's some work that's going on in this topic. Unfortunately, you would need a time machine to go see this talk, because it was earlier, but it was yesterday. But Lauren Steinley is a PhD student working with me who's on the job market, and this paper has details about an approach for dealing with data uncertainty, and also uncertainty from different assumptions that you might make about models, and how to resolve that ambiguity. And with that, I want to finish off here. I just want to leave you with 3. See how bad I am at judging how long this is going to take? But you've got the slides, so you can check it out. If there's 3 takeaways, I want to say, this was about sequential decision making, but operations research in general has an important role to play in understanding and advancing medical decisions, and there's a long way to go. We haven't been big contributors from the medical perspective, but I think we will be. Observational data is an extraordinary resource. It's just a massive amount of it. In electronic medical records, it's just sitting there. It's a gold mine, but there's all kinds of problems with bias. And when I don't like to think of them as problems, I'd like to think of them as opportunities for new research to try to unlock the value of that. And so there's incredible opportunities that are out there. If you're like a junior faculty member or a PhD student, you could be the world's leading expert at the intersection of operations research and an important disease. So this is a great time to work in this area. These are some folks that helped me with the tutorial, and I presented some of their examples. This is funded work in part by, motivated by work that I did that was funded by the National Science Foundation. I'm very grateful for that funding. And you can find the talk and stuff on the website, pictures of my fishing trips, whatever you want. I love talking about sequential decision making under uncertainty, and I love talking about fishing. So if you want to contact me, talk to me afterwards, anytime, I'm available. And thank you very much for your very great attention.